I am AI. I am a creator, freeing our imaginations and breathing life into our wildest dreams. I am a guardian, keeping us safe on our way home. And wherever our curiosity takes us. I am a visionary, anticipating the needs of others. And simplifying our busy lives. I am a protector, keeping our most magnificent creatures out of harm's way. And helping our heroes make it home safely. I am a healer, decoding the secrets from within and providing precision when every second counts. I am an innovator, finding smarter answers to complex tasks, working in harmony to lighten the load, and driving perfection in everything we create. I am even the composer of the music you are hearing. I am AI, brought to life by NVIDIA, deep learning, and brilliant minds everywhere. Ladies and gentlemen, please welcome NVIDIA's Vice President of Accelerated Computing, Ian Buck.
Thank you, everyone, for coming to GTC. This is an amazing event. I've been coming to it for I've had it 3 years now. This is my second time giving this keynote. I'm super impressed with the attendance today. We have over 3,500 registrants. We're literally sold out, so thank you very much. That's 30% more than last year. So thank you all for coming. There's over 110 sessions with over 186 speakers. We have over 50 sponsors, and our DLI trainings, which we'll talk about later, have entirely sold out. So it is great to see DC becoming basically an East Coast hub for AI innovation, and this conference being a place where all the different AI innovators or people interested in getting started with AI can come and learn and understand and figure out how to take what they learned from GTC and bring it back to their agencies, bring it back to their industries, and make AI real. For this talk, I'm going to go through and just explain how we can help do that and how we can help accelerate AI and really put AI to work. To begin, let's start with some perspective. We all, maybe, hopefully, many of you have heard of the first discovery of AI, which was around image classification. That was one of the first AI networks ever built. A guy named Alex Krivetsky back in 2012 was working on this thing called deep neural networks. Neural networks were long since forgotten or dismissed part of AI. He quickly won a competition called ImageNet and crushed the rest of the computer vision field with a network called AlexNet, named after himself. That kicked off the AI revolution. As image classification, understanding what is inside of a picture. This is a picture of a cat or a dog or a ball. When it reached accuracies of 80 to 90%, that was enough to start taking it into production. We quickly saw the world of AI and neural networks expand beyond just image classification, what is this a picture of, to image detection, i.e. where in this picture is a cat, a dog, or a ball, and put a little bounding box around it. And we've all hopefully seen those demos as well. Modern image processing now does full segmentation. You can go down to the individual pixel level and pull out pixels of different people, their faces, and things all the way down to the individual pixel level. This is work like NASCAR CNN by Facebook and other researchers. We've basically matured in the world of image processing. The next wave to come was language understanding, and it started with sentiment analysis. Is this tweet a good tweet, a bad tweet, a good product review, a bad product review? Obviously very important to e-tail and web commerce websites. It evolved to translation. Most translation systems today are AI-based. And of course, now with auto answer. Whenever you use your phone and it's auto-correcting or coming up with an answer or suggesting lines of text in a Word document, that's an AI in process. Furthermore, AI became more intelligent with decision making. It started with basic search algorithms, replacing traditional machine learning and going into search or looking for things on the internet, to recommender systems. Most of the things recommended to you on websites you probably use every day were generated by an AI. And then further to anomaly detection. Half of the world's enterprises today rely on AI for network security and protection. And 80% of the telco executives believe that they're going to require AI to keep their network safe. AI is a wonderful tool for looking at massive amounts of data and finding anomalies, differences, and pulling the needle out of the haystack, as you will, for that. That is the basic of what built up the foundation of commercial AI today. But AI has gone way past just these simple use cases. Today we have the researchers at conferences like CVPR and NeuroIPS coming up with all new applications for AI. And they're truly exciting. Some of them are actually even just fun. I'll go into GoGAN for a minute. This was done by NVIDIA Research. They trained on 1 million images on a DGX of different paintings and painting styles. And they labeled the paintings by segmented by different kinds of objects in the paintings to allow you to interact with it. And I'll show you a quick demo of that. This is GoGAN in action. I think we have it on the show floor, and you can play with it. You can actually click mountain and draw a mountain. You can click water and draw water. You can click sea, sky, clouds. And it's been trained on 1 million images from real paintings. The result, actually, the AI then takes that information and inserts it into the image, creates the right blending between the different segments, and produces a gorgeous vision on top. Now, for those of you who grew up watching Bob Ross, it's just he was a true pioneer. And I believe he would be a huge advocate of AI if he were alive today. This is an amazing demo, and I encourage you to play with it. You can change styles. You can switch from different artistic styles. It gives you a sense of what AI can do. It's using a general adversarial network. So this is a network that actually generates pictures. It starts by generating bad pictures because it hasn't seen any. And then there's another network that's in there telling it if it's a good one or a bad one, a real picture or a fake picture. And it slowly learns over time. Amazing technology and an incredibly tricky thing to train. In addition to GoGAN, we have pose estimation. So there's multiple startups and networks that are used to do pose estimation today. By just taking this camera image, it can figure out where the different limbs are and create a skeletal model of the character. And we can use that to do, particularly in Hollywood, to do motion capture. This is some work we did to celebrate the moon landing. We actually have this demo where you can interact and be an astronaut in space. That entire motion capture experience is all done with AI with a single camera. No bunny suits required. You don't have to put special markers like you've seen in Hollywood anymore. AI can just figure it out. Reinforcement learning is a very hot topic. This is actually where we're teaching computers how to do things in simulation. This is a simulation of teaching a simple character how to do a backflip. I wish I could show you the before. The before, they just fall on the floor. And you slowly reinforce them, and you give them a score, and the AI can learn how to do a backflip by just articulating the joints and have the right physics happen to perform the backflip. Leonardo is a kitchen robot research. So one interesting aspect, and we'll talk a little bit more about robotics. Today in robotics, neural networks are being used to actually do all the motion planning of a robot. And we do this in simulation because actually training a robot in reality is quite a slow and painful process. Instead, we can do it in simulation. The simulation's on the right, the real robot's on the left. So by the time you actually train it in the computer and plug it into the real robot, it just works on the first day. It's quite amazing. The automotive space is obviously using AI in lots of different flavors, and we'll talk about that later. One of the challenges is just getting enough data to train in real-world scenarios. We're actually using AI to create virtual worlds that are based upon actual video and to create more scenarios, to create more miles. We literally need millions of miles traveled to certify a self-driving car. And we're not going to, we can do that by trying to record millions of miles of audio. We're not going to make millions of miles worth of modeled 3D landscapes. So instead, we can use AI to generate it. Semantic segmentation is also important in AI. We're actually now can do that down, not only in an image, but in video as well. Every frame, every pixel can be segmented out, whether it's road or car or tree, and that can be used to both to inform a self-driving vehicle and to recreate some of those virtual worlds so we can train on them. AI has gone to 3D now, to 3D segmentation. We can actually do 3D segmentation of CAT scans and reconstruct sort of Star Trek style from a CT image or an MRI image what the actual inside of a body looks like. This stuff is getting extremely real, and there's even more pictures that came out today, which you may see on the show floor, that really makes, in the future, when you look at a scan, you will see what the inside of your body actually looks like. That'll all be reconstructed through AI. And of course, the self-driving car challenge, which has to bring all of this together to drive a vehicle. This is the big bang of modern AI. It started with common use cases in the areas of image, language, and decision making, but now it's spanned multiple modalities, multiple use cases, and everywhere where we can reconstruct from data, AI can be that tool. So for the rest of this talk, I'm going to go through some of what's the day of the life of AI, just to explain to you and bring you up to speed of what modern AI feels like and what it looks like. And then I'll go through how we can apply this to industries. The baseline for AI has 3 basic steps, and we all should know it, but it's actually gotten quite impressive. In the beginning, we'd still have to process and gather our data. Data doesn't start ready to train. It comes from multiple sources, from telemetry data to maybe user data to inventory data to machine monitoring data. We need to combine all that and put it in a way that's digestible to train. And that process of extract, transform, and load is known to every data scientist. It's just getting a lot harder because there's a lot more data, and we now have something to do with it. We need to build the tools and build the infrastructure to construct the data to train. Once we have the data, we need to train it. Now, training has gotten harder because the networks have gotten smarter. As they get smarter, they get bigger, and they just require more computation to train. And if it takes too long to train, the data scientists just don't want to wait around. So the challenge here is the rising network complexity. Some of those language models so in the beginning, you can see here's the original AlexNet, which doesn't take very much to train. It was about, it sounds like a lot, but it actually isn't. It's about 5 petaflops. Seconds per day to train. Where you get out to GPT-2, which is the latest network from OpenAI, that can take potentially up to a week or 2 to train, requiring over 205 petaflops per day to train. And then when we go and want to deploy this, deploying AI now has moved from a PC or a server to everywhere. We're deploying AI in the data center for sure, but we're also deploying it in the robot. We're deploying it on industrial use cases, in wind turbines, and power plants. We're deploying it in autonomous robots, and of course in self-driving cars and IoT devices. So we need to build a software stack that can actually scale to all those devices now. So let's start through some of these things. Training, so the data processing step is classic data analytics and ETL, just amped up. An example here would be Charter Spectrum. Charter Spectrum is a telecommunications company, one of the world's largest cable operators. They have over 25 million subscribers and over 500,000 LTE or Wi-Fi connection points. And their challenge is very simple. I'm running a nationwide network. Where do I put my next 10,000 base stations, whether they be Wi-Fi or LTE? They collect all the data. They've got enormous amounts of data. It's 1 terabyte per day of data, and to make those informed decisions. And from multiple data sources. So before, it actually took their data scientists about 8 days to manually process and collect and make a decision on 1 day's worth of data, 1 terabyte of data. By moving to a GPU accelerated stack, with a software stack that we call Rapids, they were actually to process that 1 terabyte of data in about 4 minutes. So by accelerating what used to be a manual process, which is all based CPU-based, a file I/O based, has moved to a GPU accelerated in-memory stack, and as a result can do it in almost real time, about 4 minutes. So they can actually see from a day-to-day basis how their network's being used, where their choke points are, and make those decisions. Rapids is the stack that enables that. It's built on top of Apache Arrow, which is an in-memory data platform. The processing has moved from disk-based to in-memory based, which obviously makes it faster. And Apache Arrow is the common memory format that allows all the components to work together. And then it's coordinated by Dask. Dask is the parallel computing library in Python that turns this operation into a distributed one, whether it wants to have it on a single node or a single GPU or multiple GPUs. And then, of course, on top of that is the Pandas workflow, which is sort of the data science workflow stack. This whole stack is accelerated by NVIDIA GPU libraries. So we have a team of library engineers which are doing cuDF, or CUDA data frame modules, which move the data frame objects onto the GPU so they can be processed in the GPU's memory. It also have cuML, which is just a huge basket of machine learning algorithms that have been optimized, including XGBoost, to run on the GPU and to enable those speedups. The library engineers that work in my team take input from all of the industries, all of the people at GTC. In fact, this is one of our major product definition conferences, is to hear all the algorithms that you guys need to make faster. We add them to cuML, we release them in open source, and make them available. We also are working with all of our OEMs to put out data science workstations that have 1 or 2 or 4 GPUs in them to accelerate these workflows so they can move from the traditional file I/O CPU-based to a GPU-accelerated one. If you haven't seen a data science workstation, I believe we have some here on the show floor. They can give you live demos so you can see and feel how your existing workflow, your existing Pandas, or scikit-learn or other use cases can be accelerated with GPUs quite trivially and much faster. That's data processing, and that's only going to get more complicated as we collect more data, and we need to accelerate it. The next part is training. Now, training's gotten a lot faster. It's had to get faster because the networks have gotten bigger. It's a chicken and egg problem. Basically, data scientists are going to build the fastest, biggest, baddest networks they can, as long as they can train in about a week, because after that, they get bored and it's not productive anymore. So as we're building faster and faster systems, we're getting more and more AI capabilities, which is very exciting to see. And that's evident in the explosion in the network complexity. So just another view of networks, our original models for image processing were 26 million parameters, so 26 million connections in the network. As we go to language processing, networks like BERT, you're going from computer vision to language. And language understanding, language like summarize this web page, or tell me, or give me an answer to this, generate an answer to this question. Language is a much harder problem. Computer vision, if you think about it simply, having a network which can recognize this clicker, my eye almost does that automatically. I don't have to think to recognize that there's a clicker there. Humans have that hardwired in their brain. So do other mammals and animals. Dogs can recognize this. Even bugs can recognize basic objects. As a result, those networks are actually fairly small, 26 million parameters. And they're small. They're a portion of our brain that isn't that complicated. But if you get to language, now we're talking about a real intelligence. You actually not only have to understand what was said, but what was meant, and the meaning of it, and the symbology of it, and the conclusions of those results. Dogs don't do that. Cats don't do that. Bugs don't do that. That's the real intelligence. As a result, those networks are big and getting bigger. We haven't reached the limit. In fact, NVIDIA Research just announced Project Megatron. It's 8.3 billion parameters, or billion connections. It's actually too big to fit on a single GPU. We have to put the model across 8 GPUs inside of a server, and then we do data batch parallelism to try to train the thing across an entire cluster with 64-way data parallel. It's 24 times larger than the BERT model that was published by Google just 9 months ago. And they've proven that that's not the limit. So this hasn't overfit yet. They can continue to go up and to the right as they improve intelligence and language understanding. This is going to be the neural networks that are going to make chatbots, truly realistic. These are the networks that are going to do full email auto-completion and documentation summarization. They're going to do question and answering and for intelligent communication and conversational AI. To train the models of this size, you have to figure out how to take lots of servers, connect them up, not just physically with InfiniBand, but also from a software and algorithmic and mathematical perspective, to turn them into one sort of super GPU, to train a single model. We trained, so at NVIDIA, we actually do this. We have many GPUs in our own data center, which we use for our self-driving car exercises, but also for our own product teams. My team works on trying to build and scale up and push the limits of how far we can train a single neural network. We had this system which we call DGX SuperPod, is 1,500 NVIDIA Volta GPUs, fully connected with the Mellanox interconnect. You can see in the middle there. It's 9.4 petaflops. It's in the 20s in the top 500 supercomputer list, but it's only 96 servers actually. As a result, this network actually can train the ResNet 50 in about 80 seconds, which is ridiculously fast. But the more language models, it can do BERT in about 47 minutes, and that Megatron model in about 9 days, which is about the limit of what we want to see for a data scientist. Again, operating as one big super GPU. To make things work at that scale is complicated. You have to have the right server, the right interconnect, all of the right optimizations in TensorFlow or PyTorch in the frameworks, as well as the communication libraries, the image processing, the I/O libraries. You have to feed the beast in order to keep it busy. That whole stack, we challenge ourselves to do it as big as possible, and then we turn around and take all those innovations and push them out into open source and make them available to the market. We push them into the frameworks like Chainer, MXNet, Paddle, PyTorch, Scikit-learn, TensorFlow. I have teams working on all of these frameworks. We push them into the cloud ML services. So we enable Amazon SageMaker, or Google Cloud ML, Microsoft Azure, or Databricks to do service-based training. And then it can turn around and also make it available for inference. All of this sits on top of our AI software stack, which is the CUDA XAI for data analytics through to DL training. And then all the server and technology, the hardware parts, we make available through our OEM customers or the cloud vendors. So whether it be HP or the servers direction, from workstations to servers, or HP to Dell, or the cloud like Amazon or Google or Microsoft. So that's training. Training has basically gone to a scale-up problem. It's almost become a supercomputing problem. And today, if you're going to be doing training for language problems outside of the basic image processing, you're going to need a supercomputer of some scale. And we've put the blueprint for DGX SuperPod, whether you buy DGX or you buy the same kind of equivalent configuration from HP or Dell, that's great. But we've got training now to do world-class training, to do training in language processing, requires a pod architecture of some size in order to get reasonable results. And then inference. Inference has become, in production use cases, quite complicated because it's not just one neural network anymore. Today, modern AI uses a collection of networks, a collection of container technologies, and all needs to operate in real time. The most interesting trend right now is the trend in conversational AI. This is an area where we are talking to our devices, we're talking to the computer, we're talking to the cloud, and it's talking back to us. Simple things like who won the game last night, or what's the weather in DC, to more complicated questions about interesting in home renovations. It's interesting. Actually, it's projected by next year that half of the world's internet searches are going to be done by voice. So this is why you hear so much news about conversational AI today. It's because we're going to be talking to our cars, we're talking to our phones already. We're talking to that hockey puck on our kitchen counter. And that's how we're actually interacting with the internet and with the cloud and how we're buying things. In fact, it's projected by 2022 that over 50% of households in the US will own a smart speaker. So we're going to be talking to our devices. And that challenge has actually created this entire new field called conversational AI. And it's in production today. No one does it entirely end-to-end yet, but they are all moving toward it. And you have a whole list of neural networks. The first neural network is denoising, actually taking the noise out of a speaker system. The device wants to be cheap. It doesn't have a lot of echo cancellation in it. We're going to use AI to actually process the audio and to identify the speaker. One of the first things they do actually is figure out who is speaking and try to identify who it is so they can personalize the response. The second is the actual speech recognition of ASR. There's a whole list of different neural networks that are being used for this today that are all open source, but they're all using AI or CNNs to do this work. And then it goes into a language model, where the language model actually predicts what is actually being said, and they classify the question. Is this a question about weather? Are you buying something? Are you doing a general information search? And that tells the cloud which search engine to actually fire off. As it does the actual search and through a recommendation system, which again is another AI, it comes back, and typically these are question and answer use cases. So it pulls down a Wikipedia page about interior lighting, for example, and it's got to come up with the answer. So you've asked a question like, what are the different types of lighting for a living room? The search engine may come back with 10 different pages about lighting in a living room, and then use a neural network like BERT to scan through the document, running the neural network on every paragraph, coming up with an answer. And it will tell you specifically where in which document and which section of the document has that answer with a certain confidence score. That's fundamentally what BERT does. It's one of the largest networks. It's over 300 million parameters, so it's very expensive to run. In fact, they can't run it on all 10 pages today. They wish they could. They have to use simpler statistical methods to pull out the right content. But as they get better and they accelerate their workloads more, we expect that to improve as BERT gets applied to the entire document, not just sections. As the result of that, then it goes to text-to-speech. So you have the answer. Now you got to make a voice that sounds good. And that's actually used to be, we all used to the robotic sounding use cases we had in our computers. And this part's gotten really good. So the first step is text-to-speech. So in comes the text. Out comes a spectrogram, which is the audio. Networks here have very fun names. One of them is called Tacotron. I think it's like Talking Tron, but they call it the Tacotron. And that outputs a generic robotic voice. And then it goes through a separate phase, which is called a voice encoder. The voice encoder is really what made voices sound good. These are neural networks called wavenets. It takes a generic sounding robotic voice and adds all the breath notes and all the inflections to make it truly human. And the results here, the wavenets, is why you're experiencing in like Siri and Cortana and Alexa, why they sound so good. In fact, here's a quick demo. This was done by folks at Google who working on wavenets off of a MEL spectrogram. They're going to read this sentence, and they're going to read this sentence twice. And one of them's a human and one of them's a computer. See if you can tell.
George Washington was the first president of the United States.
That's one.
George Washington was the first president of the United States.
No idea. Just none. So that was actually a computer-generated voice, and then a voice actor came back and read the sentence. So it is truly, in fact, Microsoft has a test. You can go to their webpage and you can test their Cortana and see if you can actually tell if it's human or fake. I've tested it at work, and it's been 50-50 every time. So, but AI is really what made this possible. In the world of inference, it is a complicated end-to-end chain, and the important thing is that workflow has to all happen in about 1/3 of a second. If I can't run all those neural networks and do all that search and get the audio back in 1/3 of a second, the user experience just falls off a cliff, and people won't use it. So one of the big challenges in production inference today is to build the end-to-end workflow that can run in real time, can run multiple networks, and that's why there's so much pressure to use things like reduced precision, 8-bit integer operations, and new neural networks that are faster and leaner and meaner in order to do real time. So I've talked about the 3 steps of AI and where we're going. Certainly our data is increasing, and we're moving to GPU-accelerated data processing for ETL and data analytics. Training has become a scale-up problem of building supercomputers now for doing training, and companies and countries are buying pods of GPUs to do training of neural networks, especially for language processing. And then in the world of inference, it's all about real-time and connecting multiple containers together to connect to end-to-end. That's interesting, and that's kind of what the capabilities are. But the challenge is, how do we take it from innovating and doing all these innovations in AI to actually applying AI? And what we haven't seen yet, we've seen examples of, is how can AI really get into the industries that everyone here is serving, whether it be public sector for disaster and release, or autonomous vehicles, or autonomous robotics, or AI into industrial use cases or infrastructure, to finance, to retail, to even scientific research and healthcare. There's a gap, because I can't just download TensorFlow and expect a healthcare data scientist to be able to figure out the neural network to discover which genes cause cancer. Those don't exist today. In fact, most of the AI research and AI development is being done by companies like Google and Facebook and Amazon, who we've all heard of, who have the capability and the compute and the talent to invent AI from scratch, like they have for all these amazing use cases. So our challenge, and NVIDIA's challenge, and one of my challenges, is how can I bring AI to industries and activate it, truly make it possible to bring this capability to these industries and accelerate them faster. Because our existing software that we have access to today, the TensorFlows and the PyTorches, are insufficient. The models that are being published in research can't make their way into production, because there's a knowledge gap and a capability gap of the software stacks that exist today that just prevent that from happening. So let me walk through a couple of use cases and areas that we've invested in to help advance AI into the industrial use case and really put AI to work and make it possible, and bridge that gap, particularly in the software world, of what is the right software for the healthcare person, or the finance person, or the person doing a smart city application. Let's start with healthcare. Healthcare certainly is a fascinating industry. One of the obvious applications of AI is medical imaging. Here we have tens of different modalities, from CT scans to X-ray to MRI to ultrasound. This area is ripe for AI just because of its image nature, of understanding images and what's inside of images. In fact, it's a growing problem in the United States. In the US, we have around 50,000 radiologists in hospitals, but a typical radiology department has to process about 8,000 images every day. So if you do the math, and the 50,000 radiologists, there's a critical shortage, because this actually works out to about 4 seconds per image per radiologist, which is a frightening number in terms of getting a scan. They really only just have only about 4 seconds to help identify and make a diagnosis. Here, AI can help. It can help be a place where we can do AI-based segmentation and imaging to assist that radiologists, unfortunately, to make sure they don't miss anything or accelerate their workload to save time. And in a more broader place, in some cases, healthcare is full of data. There is over 30 million publications in PubMed. They're adding literally 3 papers per minute, or 1.5 million new papers or citations every year. So we have a wealth of data that is potentially going untapped, because it's impossible for every researcher to read every paper, or even potentially the right researchers in the right field to see every citation. Can AI help in this space? And we believe it can. But let me go through one of the things we're going to do to help gap from TensorFlow or PyTorch to applications of AI. At NVIDIA, we've been building this technology called the Clara SDK. Clara is our project to help accelerate and bring to market AI specifically for healthcare. It has 2 main focuses, Clara imaging, and we've expanded it recently to include genomics. But in the imaging use case, an imaging workflow is actually relatively simple and it's familiar to many people in AI. You have unlabeled data, you have some annotated data, and we can use the Clara SDK to train a system on the labeled data to learn how to recognize certain things inside of images. And then turn around and use the Clara inferencing capabilities to deploy in the device or at the workstation. And it doesn't matter. Remember, inferencing wants to happen at multiple modalities in multiple places. So Clara runs on the embedded device and on the edge server in the data center, or it can run in the cloud, wherever it wants to be deployed. The applications inside of Clara is specifically focused on AI annotations. It actually includes a medical model archive. We have 13 world-class pre-trained models already designed to extract major organs from medical imaging data. And it actually has a specific tool in it called transfer learning, which I'm going to talk about in a second, that allows you to extend the capabilities of Clara to your medical device or your particular disease that you want to look for. Transfer learning is the new thing in image processing for AI that's really powerful. We've already discovered the vast majority of neural networks necessary to process images and process volumetric data. The question is, how can you apply it to your particular problem, your particular disease, or your thing that you're looking for in your image? With transfer learning, what we can do actually is take an already capable network. This one here, which is included in the Clara SDK, can extract the volume of the heart out of an image, and we want to add other capabilities. We want to look for specific kinds of tumors, for example. So we can start from a pre-trained model which already is recognizing organs and train it looking for cancers. Not by starting from scratch or designing a new network and training from the beginning. It took over 250,000 images just to get to this level of capability. And we may not have 250,000 images of what we're looking for. But with transfer learning, we can take that pre-trained model that's already intelligent enough to recognize heart and give it images of a particular cancer that's been labeled. By doing so, we can actually, in this workflow, we only need about 7,000 images in order to add a new class to an existing model. Compare that to the 250,000 we needed to train before. It's also way faster to do transfer learning than to train from the beginning. It took over 19 hours to train from scratch, but applying transfer learning, we can do it in under half an hour. So this transfer learning toolkit is included in the Clara SDK. It's also plugged into the open source Kubeflow environment, which developed by Google, which supports GPUs. And it actually can give more of a WYSIWYG training workflow for the healthcare data scientists, so they can do the transfer learning training, run it in the cloud or on their on-prem server, and watch the training curves go as they go and tweak and model the parameters to improve the accuracy. So this kind of workflow, taking pre-trained models in a modality they already understand, already can process medical images like DICOM, already have pre-trained models and apply their data, use more of a friendlier WYSIWYG kind of interface, which is using open source tools like Kubeflow and TensorBoard with the transfer learning toolkit plugged right in the middle, makes it much more approachable to the healthcare industry. And this use case is not unique to healthcare. In many of my conversations that I have here in DC, it's all about, hey, how can I apply, I just have an image use case that I want to learn, but I don't know how to start, and if I just download TensorFlow, it doesn't tell me how to get there. Transfer learning is your answer. Take a pre-trained model. We have hundreds of them on our NGC website. And we have transfer learning toolkit examples and walk you through it to take an existing model, whether it be healthcare or object recognition or object classification, and retrain that model with the data sets that you have. So this use case applies to many use cases in federal agencies and in industries, and transfer learning is a new way of doing training today with image processing. So switching gears, we talked about healthcare. Healthcare needs a new workflow to make it possible, and the Clara SDK was designed to do that. We're having great success with it in the market. But let's switch gears and talk about smart city and 5G. 5G, you've all heard about 5G. It's very exciting. It's 4G plus one. It's so exciting that people don't know why it's exciting. It actually is exciting, and let me try to explain it in simple terms, okay? And the reason, there's a couple things which it makes it really exciting, especially for AI, which is not a connection everyone makes, but it's actually changing how we're going to experience things. It is a revolution. I don't use that word lightly. I mean it. It's effectively 1,000x more bandwidth. Bandwidth doesn't become a problem. I mean, you can download. People have talked about downloading seasons of Stranger Things in seconds. Yes, you can do that. Effectively, it unlocks the bandwidth to any device or any access point. I believe in the future our homes will be connected not with cables or phone lines, but we'll get our internet through Wi-Fi, through 5G. So the bandwidth problem effectively goes away with 5G. It's also designed to be ultra reliable. because it's so high def and so high frequency, it has to really nail that frequency hopping capabilities. And they designed 5G to be ultra reliable, so you always have a connection as you move through a building or through a city or in a complex environment. So you can think of 5G as good connected like a wire. You don't need to worry about the drops. It's also extremely low latency. So we're going from tens of milliseconds of just ping times, or at best, down to 1 millisecond latency to the towers. That's really low. And, in that conversational AI case, I need 300 milliseconds of latency. But it gives us an opportunity to actually send enormous streams of data and respond in real time, literally, the response time of 1,000th of a second. That opens up another use case for actually moving some more of the intelligence from devices closer to the edge, and a lot of devices. So 5G is going to be able to support, we're maxing out maybe 100,000 per square kilometer with 4G. You can go up to 1 million devices in a square kilometer with 5G. That's a lot. So you're going to have a huge number of devices connected with 5G with effectively infinite bandwidth. They don't need to worry about bandwidth. They have 1 millisecond latencies. And it's an ultra-reliable connection. So effectively what that means is all of that promise of IoT can be made real because I can make my device incredibly cheap and low power. It doesn't need to have any intelligence. All it needs is a 5G connection, and I can move all of its AI, all of its processing, anything it wants to do to the edge. As a result, 5G is enabling us to build low-cost, ubiquitous, everywhere IoT devices, whether they be cameras or doorbells or shoelaces, if you will, that are connected and as intelligent as an entire data center. That's the promise of 5G, and that's really, and the technology is being unlocked in that revolution. As a result, whether it be IoT, we're going to see new AR, VR, because we can process all this work in the cloud. Cloud gaming is becoming much more realistic with the bandwidth and low latency ping times. Certainly interesting to NVIDIA. The robotics use case, robots now don't have to be intelligent, self-contained devices. They can move all their intelligence to the edge and literally support trillions of devices. As a result, the edge is going to change too. The current edge is a cell tower and maybe a base station that's very fixed function. There's hard boxes that do one thing, either voice communications or data communications, or we all have like multiple devices maybe for watching TV or cable modems. They're fixed function. With 5G, as we move all these capabilities to the edge changes to be much more software-defined. It becomes a generic sort of mini data center, if you will. And you want to put it right at the edge because you want to be able to do those use cases which require 1 millisecond latencies. So what we're seeing is basically the data center moving more closer to the edge. We're still going to have the big data centers that you've probably seen for all the search data and where our queries are going to go. Those will exist. But the edge data center becomes much more intelligent, much more capable to run all these workloads, to provide all that intelligence. Remember that hockey puck on your kitchen counter, that wants to be $0. That wants to be the lowest cost possible because it wants to be ubiquitous. And with 5G, we can move all the intelligence, all the AI to the edge and make that possible and just multiply that by anything robotics or anything IoT. So 5G is truly revolutionary, and it's happening now. We've actually announced new servers specifically for the edge. We call them the EGX Edge Supercomputing. This is a server that can have 1 to 4 GPUs in it. It's being built. All the OEMs are going right after the edge, from Atos to Dell to Fujitsu to HP to Lenovo, Quanta, and Supermicro. You see the cloud guys doing it too. So just yesterday, Microsoft announced their Azure IoT Edge and machine learning stack and Azure Edge stack, which has 4 of the NVIDIA GPUs in it, specifically for that. So the cloud guys are also getting into the edge play, along with the telcos. This is a great opportunity for the telecommunications company to become their own edge cloud infrastructure. What do you want to run on the edge? You want to run everything on the edge. You want to do the AI for IoT. You want to be able to do gaming. You want to do video. You want to do voice. You also want to manage your 5G network. You have 1 million devices in a square kilometer. The frequency hopping is pretty complicated. In fact, those capabilities are actually moving from fixed function or even FPGA-based to GPU-based. And we have a new SDK, which we call Aerial, It's a 5G stack for doing the VLAN work, and to accelerate the 5G stack and make it possible sooner. One of the use cases, again, we talked about needing a different stack to enable the edge, is smart city. So with 5G, we can place high-definition cameras anywhere. There'll be simple camera devices with a 5G modem, and they're connected to the edge for doing the processing. So as we ramp our smart city use case, we're going to be connecting cameras to 5G. How do we now build that AI stack for smart city? In this use case, specifically traffic monitoring. You can't just and make it a real-time workflow. It needs a different stack than what we use for training. It's what's publicly available from PyTorch or TensorFlow. We've been developing this stack called DeepStream, which is a software stack which runs on those EGX servers that can process video. It can do basic image processing because you typically want to process the image even before it goes into AI. It then can do the real AI processing with a software library called TensorRT for real-time tensor processing with AI, and then apply additional graphics on the results, generate all the metadata, label data, and then encode it back into a video again, because we want to ship it somewhere to an operator to alert people. Smart cities, a single EGX server can support over 140 HD streams. These are 1080p, 30 FPS kind of video cameras, high resolution. We've been working with, have a pilot going right now with Dubuque, Iowa. They gave us access to 200 camera feeds, which we served with a single EGX. Each camera is processing about 30 to 50 vehicles at a time. And what we're doing is doing sort of 10,000 vehicles across the pilot. Each camera is actually first labeling all the vehicles, cars, trucks, et cetera. And then in addition to all the labeling, once we know where the car is, and where it is on the road, we can look for anomalies. So we've built an LSTM-based, rule-based AI that can detect when a car is maybe not doing something it's supposed to be doing, and flag that to an operator on the right. So this DeepStream stack is actually available right now on NGC. This system, and in fact, we found some. So you can see there's 140 cameras, kind of what it looks like running on the EGX system. This is, again, all processing on the GPU. We're pretty good at processing video, so that helps. And then we find stuff. So this actually happened. I guess some guy decided to go the wrong way and further decided to keep on going. Just keeps on going and keeps on going. Just not a good idea. So this happens. Now, before, without Smart City, it would have happened, and hours later, a police officer would have come and probably found that woman's camera and tried to chase down that person. Meanwhile, maybe that person kept going, which is a frightening thought. So with a Smart City application, we can actually alert immediately, and you can see that on the right, we were actually able to track and alert the operator that there was a vehicle going the wrong way on a highway, which is quite scary. This pilot was successful. It's actually going to go operational in Dubuque in December, so next month. And it kind of shows with the capabilities which you can do with EGX for Smart City. And again, using a different software stack targeted at the industry, in this case, smart cities. Like healthcare, like the Transfer Learning Toolkit, it's not just for healthcare. This is not just for smart cities. These capabilities can be applied to your own industry. And the reason we do these GTCs is to share this knowledge and show these examples so you can download DeepStream, or the components of DeepStream, if you will, they're all open, to apply to your own use case. And one particular use case actually has been this TensorRT stack for doing real-time inferencing. But processing videos or looking at pictures on a manufacturing line in real time, that's a use case that's happening everywhere, particularly in manufacturing and processing. So I'm pleased to actually announce today that this same technology was, we partnered with the US Postal Service, and that they've announced that they're actually adopting NVIDIA's AI technology, including DeepStream, the TransferRT, and through our NGC containers, to accelerate and boost sorting efficiency. The US Postal Service is the world's largest delivery service. They process over 485 million daily mail every day, 146 billion packages of mail annually. By using AI, they've actually been able to increase their sorting efficiency by 10x faster than they could do before, and at the same time, improved accuracy. So they're going to be using this for improving their sorting speed and sorting efficiency and accuracy. This pilot actually was successful that it's actually being rolled out to 200 processing facilities and is expected to go operational by 2020. So very excited to see a US agency really leaning into AI. They have a cool problem. They just have to process your mail as quickly as possible and understand it on the line. And by working with NVIDIA, we've helped them accelerate that work, and we're very excited to see a US agency like the Postal Service investing in AI. And I hope that inspires you and you all to think about how DeepStream, the stack, and how image processing could apply to your own use cases. And there's certainly experts here in NVIDIA that can talk more about the technology and what's being deployed and what's capable today. Thank you. So we've talked about healthcare, we've talked about 5G, we've talked about the industry stacks necessary to make them successful, whether it be Clara or DeepStream or foundational components like EGX. Let's switch to self-driving cars. I know it's a hot topic. It's actually one of the hardest, which is why we don't all have self-driving cars today, because it's incredibly complicated. At NVIDIA, we have a fleet of self-driving vehicles, which we both use for collecting data and testing our self-driving capabilities. We ingest and create literally petabytes of data every week that needs to be processed by our own team of labelers and processed by AIs. So we have to curate all that data. We have to label it, put bounding boxes. Some of the bounding boxes are done by AI, some are done manual, some is done by AI, then checked by manual to actually create all the data. We have literally thousands of GPUs doing training every day, supporting the hundreds of data scientists which are developing the self-driving car capabilities. And then we have to replay it, the capabilities in often on the road. So we play back the video where there was a correction or a driver had to intervene and see if our new AI could correct that or make the same wrong decision, make the right decision. This whole thing has to be verifiable. We have to be able to go back and figure out when did we insert into the neural network bias that may have created the wrong decision. So the whole thing is we maintain traceability through the whole experience. So the whole thing is logged, and we can backtrace to figure out where we went wrong. And then, of course, we can't train everything in the field. We have to augment it with simulation. So we actually run many millions of miles in simulation to test the vehicle. This end-to-end workflow needs a stack way more complicated than just the simple frameworks. Each one of them has its own custom stack to make them capable. But the results are really amazing. This is our car. It runs, the module in there is called Pegasus. It actually has 2 Volta GPUs and 2 other Tegra SoCs, and all of those are the camera connections you can see there. It's basically an AI supercomputer inside of every autonomous car. Every neural network in the drive stack is handling thousands of conditions. It's gathering, processing hundreds of petabytes of data, and the whole thing is logged for traceability and safety. I could explain how it works, but we have Netta. I have a video. Netta works on the self-driving car. She can describe to you all the different neural networks in action much better than I can. So let's listen to Netta.
I want to show you our perception functionality already in action in the car. And perception is basically what enables the car to see. We take in raw sensor data and translate it into semantic understanding of the world, of the scene that we're in. So take a look at that happening on our front camera. We have DriveNet detecting obstacles, the bounding boxes around the cars. We have WaitNet detecting the intersection, the yellow box around everything. WaitNet also detecting traffic lights and traffic signs, and LightNet is classifying traffic lights stayed correctly as red. We also have sign classification going on using SignNet. At the same time, DriveNet is detecting pedestrians in the cyan bounding boxes on the far side of the intersection. We also have OpenRoadNet, tracing out the free space around obstacles on the scene. And on top of that, we have our object tracking from frame to frame. You see the track IDs on the top of each bounding box. We also have our camera-based DNN distance estimation running, so you see the distance in meters displayed at the bottom of each box. ClearSightNet is also running in the background, assessing whether and how well the cameras can see in our 4-camera surround perception setup.
Now we're in autonomy.
We have just handled another lane merge, and we are going to have a little bit of grade profile changes in the road coming up. Right there, this is why it's important to have calibration continuously running in the car. We see the lane handling mode move into split mode. The car needs to correctly take that lane split to the right to not unintentionally exit the route. Path Perception Ensemble is now navigating another high curvature interchange. We see the center path staying green. And we are now moving right into that third maneuver. This is a lane change under time pressure. We don't have a lot of time here to move from the right lane into the next adjacent left lane in order to not incorrectly exit from our planned route. So here we go. We're switching from keep mode into speed adaptation, into change mode, and landing in the center of the target lane to complete that set of maneuvers. And we are now going to complete the rest of our autonomous route and head back to the garage.
She's great. And I tell you, if you're in the car, it is that emotional. I've done that merge multiple times. I live right over there, and it's not easy navigating in California highways with your hands on the wheel. Just watching someone with their hands like this the whole time and having the car do a lane change like that is your heart drops to the floor. But it's very exciting. This is kind of shows you the kind of that whole interaction at the end was completely autonomous. This vehicle actually can go from NVIDIA out to the highway, drive all the way around the Bay Area, and come back in the garage entirely autonomously now. It does that through a whole list of different networks. You have DriveNet, OpenRoadNet, LaneNet, WaitNet. They're all working in concert, making path planning decisions along the way. For a self-driving car, you not only need to be able to have the car drive itself, but the car needs to be self-aware of the driver as well. Our future self-driving cars are going to be interacted in a different way. We're going to want to talk to our cars just like we talk to our phones. That's also part of our Drive IX stack. And then, of course, the core and capabilities. So this is a much more deeper, richer stack that is than just the traditional inference or training. And it gives you an example of, again, another industry that needs another stack to make this possible. But just as cars are autonomous, they need to stay on the road and not hit things. We also have the flip side of robots, which are designed to hit things, but safely. So robots are the next area where this capability is actually going to be deployed. And robots in the past were very good at repetitive tasks. We've all seen the robots working in factories. They typically are simply repetitive task machines. They were taught to do things once, usually with manually articulated teaching, and just repeat that process over and over again. They're also put in big cages because they're not intelligent. If a human got in there, they could get seriously hurt. The future of robotics is all about interaction and working with the real world. So in the real world, you have variable objects like cleaning up a kitchen counter as a common use case, which is, there's no one simple repetitive task. You have very dynamic environments. They have to work, whether they be in hazardous environments or robots that we're going to sell and send to Mars to build the future Mars station. They need to be able to work autonomously in dynamic environments. We need to trust them to be able to do that. And third, we want to get robots to the point where they'll be safe in human collaboration. In fact, there's startups doing that now, where the robot is trying to do a task, but also can interact with the human safely to work together. That is what is these are the things that enable robots to take the next step, and they're going to need AI to do that. And they're going to do that and enable multiple industries, particularly in retail. Retail is an area which is very labor intensive. You just spend, a staff member in a typical store might have 50,000 products. They spend about 100 hours a week just scanning the aisles looking for things that have sold out. I mean, you might have cash register data, but some things they always have to do an aisle check, and those aisle checks can take literally of someone 100 hours. That can be something easily done by a robot. Furthermore, we all started seeing robots and more interactive provide new kind of customer experiences. So while they're helping this woman find something at a hardware store, they could be scanning the aisles looking for things and want to work in a safe environment. In agriculture, John Deere's done some great work. I showed it last year on pesticides. So this is actually a robot which uses a downward-looking camera to detect whether that little green sprout coming out of the dirt is a weed or a piece of lettuce. And if it is a weed, it classifies it and squirts the pesticide only on the weed, never touches the lettuce. By doing this, they can actually reduce pesticide use by up to 90%. as an example of how robots can be, agriculture can be revolutionized by AI. And then delivery. Delivery is actually interesting. We've all used perhaps DoorDash or Instacart to get our groceries or our dinners. This is becoming its own industry. There's actually restaurants now called ghost restaurants. They actually don't have a storefront. They're just only available through DoorDash or on the web for click and order your home delivery of your food and dinner. In fact, many of those restaurants, it's one chef with like 5 restaurants. So he actually has a couple of Mexican dishes, some Indian dishes, and other stuff. This is the new way we're actually going to be, new industry of ordering food. It's actually becoming it's projected to be $100 billion for the home food delivery market. And to get there, we can rely on cars and drivers, but that, of course, adds more cars to the street and adds significant cost to that experience. With robotic delivery, first, all these devices are electric. We're taking all those vehicles off the road, and also can improve the economics and making that business viable, which it is questionably viable today. So the question is, what's the software stack? How are we going to get these robots capable and activated? And at NVIDIA, we've been actually working on our software solution called, hardware platform called Jetson. Jetson is an SoC. It has the same GPU architecture that's in the big GPUs, that's in the DGXs. It can run the same CUDA, the same TensorFlow, the same software stacks that you can run in that's running inside of the hyperscaler's data center, can run on those devices. That Jetson Nano there is $99. We price it and put it out that way to enable activate this market. And in fact, it is being used today in many of these use cases. The hardware is one part, but you need a software stack. A robot needs to be able to do things like depth estimations we talked about. It needs to do object detection. It needs to do pose estimation. A lot of these robots we interface with hand gestures or tell them to go places or say stop. It needs to do path planning to make decisions and do autonomous navigation. Our Jetson SDK is designed to do that. It actually has all of our inference, computer vision, core computing libraries, and graphics and multimedia and sensor stack to enable that. And then we enable an ecosystem to provide all those software models and, again, make it freely available. The other part of robotics, as I mentioned before, is simulation. To teach a robot how to do something, it's very painful to do it in reality and potentially could damage the robot or other things. So most robotic robotic training is done in simulation, and that's done with the Isaac SDK. This is a screenshot of that. These are 2 robots being trained in a virtual environment on how to pick up simple blocks. In this case, they chose Minecraft blocks. But this actually is a simulation, and this robot can learn how to pick it up and learns how to articulate its joints to successfully pick up a block without hitting another block. And the AI can learn how to do that very fast, in real time. And actually, we can train thousands of robots in parallel and aggregate their learnings together. That's what the Isaac SDK does. It has this virtual environment that can emulate the sensors and the physics to actually, so the first time you actually run the robot, it can work the first time out of the gate in the real world because you've trained it on thousands and millions of hours in the simulated world with the Isaac SDK. This whole ecosystem is actually being gobbled up by the startup community. I can show you a quick video of all the things the startups are doing. Some of them are here at GTC. It's truly amazing work. Again, packaging, picking up boxes off a random pallet. Warehouses are deploying AI robotics for sorting. Inventory management, again, the same sort of shelf counting, looking for items, order fulfillment. And in-store. And home delivery. This is going to be an exciting time for robotics, all powered by AI. If you're interested in the robotics field, definitely check out our Jetson SDK. It's $99 nano. And also what everyone else is doing. So all this software stack is available. You can go to ngc.nvidia.com to download it and get started. What's going to make the next generation of AI possible is a verticalization and optimization of our software stacks targeted at these industries. We have enormous amount of capabilities in AI. That's been proven, and I've shown you some great demos today. But what's going to take it to the next level is vertically focused industry AI platforms that allow the healthcare data scientist or the smart city engineer to get access to this technology. The AI inventors are all being gobbled up by Google and Facebook. What we need to do is help bridge that capability with a software stack that speaks their language to make it possible. And that's what NVIDIA's been focusing on, and what the industry's been focusing on, is to make AI more real. So I've talked through Clara and Metropolis and Drive and Isaac and Ariel for 5G. We also have been doing the same thing in the media and entertainment space, in the graphics world, with a software stack called Omniverse. That's actually a rendered image, not a real picture. So industries are going to be transformed by AI, and as a result, as industries get transformed by AI, so do economies. McKinsey projects that AI is going to deliver or increase global economic activity by 13 trillion by 2030. And that doesn't go unnoticed by nations. We are tracking over 35 nations, all with national AI strategies, which represent 90% of the world's GDP, to figure out that these nations recognize that AI is going to transform their industries and transforms their economies as a result. So the competition in AI at a national level is existential. Our own national AI strategies to maintain leadership have been outlined by the US government and have done a great job. We are working toward a national set of AI standards, particularly in transportation. Right now, every state kind of has its own policies about self-driving vehicles. If we're going to make self-driving vehicles real, we need to bring those together so we can have one standard and don't have to allow our vehicles to travel from state to state. Clearly, public-private partnerships work in this space. Great example of that was the USPS. Present a problem to industry to go solve and embrace them, and we have the people and the talent that can help bridge the gap, or the software stack to do it. And if we don't have it, we'll add it. These conferences like GTC, for me, I have my own product management team for AI, the place I get the input of what to add to Clara or Metropolis or TensorRT or some of even our low-level libraries. Please give us that feedback. But public-private partnerships work. You don't always hear about them because they're not always public, but they're the things that actually help bring the talent, because we're highly motivated to bring AI to your industry or your company and make it possible. And all those people are here at GTC, so if you see them with an NVIDIA badge, please talk to them. Certainly, open data sets can be a way to activate the industry. You may have heard of the Netflix challenge. Netflix offered anonymous movie watcher data to figure out what's the next movie you're going to watch, or build the recommendation systems. The current winners are obviously AI-based, but the federal government is sitting on massive amounts of data. And through the Open Data Act, in conjunction with the American AI Initiative, we can actually give those AI researchers those challenges. So if those of you who are on that data find that challenge and provide that data, the research community is just itching for someone to be famous to solve a problem for the federal government. We are starting to see AI infrastructures being built, but it's small. It's still nascent. We have a couple, actually the largest supercomputer in the US, the Summit supercomputer, which has, we worked with IBM, which is built on NVIDIA Volta, is a 3 exaflop AI supercomputer, which is amazing, but it's only one supercomputer. To do AI, we're going to need to bring AI computing ubiquitously to all the agencies, to all the labs, to all the industries to make it possible. So we definitely need that to see that investment continue to grow. And finally, workforce training. We've lowered the barrier to train by bringing up these industry-specific stacks, but we still need to teach AI what it's capable of and the basic data scientist methods. It is teachable. And in fact, here at NVIDIA, we've been pioneering with the NVIDIA DLI, Deep Learning Institute, to get your workforce ready. It's hard to hire AI talent. It's really hard. But it actually is quite capable to retrain your existing workforce. And that's what DLI has done. Every DLI workshop, unfortunately, at DC has been sold out. We have over 450 people that are being trained here at DC. But we are announcing new courses. In fact, we have 12 new DLI courses announced just this week. We've trained over 180,000 people for AI. So if you find yourself short on workforce, go to NVIDIA, learn about DLI, encourage your teams to go take a DLI training course. We also have an ambassador programs for university. We'll train an ambassador to teach their own DLI courses, and we provide all that teaching material free once they qualify. So they can hopefully bring it into academia and curricula. So that's the body of my talk. My goal and my mission is to help put AI to work. Not just do amazing demos and come up with new networks, but to help move industries to adopting AI. We are certainly seeing the technology advance, and we're always making sure that we have the latest capabilities to process the data, the right infrastructure, and capabilities to train the largest networks possible, and deploy it, whether it be at the IoT edge, the telco edge, the data center, or even the workstation or a personal device. We're pioneering on vertical industry frameworks. These software stacks bridge the gap between TensorFlow and PyTorch download to actually building an MRI, a scanner that can segment or detect the cancer. That's vertical stack is what's going to help bridge the gap, and I encourage all of you to try it and give us feedback on how we can make that faster. And finally, getting started. This actually is a picture from yesterday of one of our DLIs. Everyone's got their heads down, clearly learning. Take a DLI. They're certainly engaging and hopefully more fun than that picture shows. But thank you all for coming to GTC. You're already taking the right step by being here. Learning in AI is a community experience where it's happening, and this revolution is happening in real time. It's happening faster than we can even keep up with it. So by talking to your colleagues, talking to your peers, coming to a GTC is the place where you can learn and figure out how to apply it to your industry, your agency, or your problem. Thank you all for coming to GTC, and I hope you have a great show.